So hello and welcome back. Today will be lecture 5-1A on Bayes filters or discrete filters, and our learning objectives include the following. There will be a review of Bayes filters and the models, which we know we have a sensor model and a motion model. How to use Bayes filters for probabilistic localization when we're talking about discrete filters. Describe creating discrete filters, model as a histogram. Introducing the discrete Bayes filter algorithm, which we will do an example of in a subsequent lecture. Summarize examples for using discrete Bayes filters with octrees, grids, and histograms. And describing representing posterior beliefs through histograms. And finally, we will discuss trade-offs between the coarseness of the grid versus a trade-off for accuracy and computational efficiency. So recall that our Bayes filter and model was given by Bell of xt is equal to eta times the probability of zt given xt times the integral over all possible states of the probability of xt given ut x of t minus 1, the belief of x of t minus 1, the derivative of x of t minus 1, where this part in the integral is called our motion model and the part outside the integral is called our perception model. And eta is called our normalization constant. So in mobile robot localization, we can have grid-based localization, which we're talking about today, which uses a histogram filter to represent the posterior belief. It approximates the posterior by using a histogram filter over a grid decomposition of the pose space, where grid localization is equivalent to a general Bayes filter, except that there is a discrete nature to the representation. And the benefit in doing this is that it's not as computationally expensive as obviously integrating over a whole continuous grid field. The robot starts out with a global uncertainty about where it is in the world, which means it's constant over all possible locations, and that's represented by a uniform histogram. And then as the robot senses and moves, the corresponding grid cells raise their probability values based upon what the robot senses around it and what we know about the map given about the world. So here's an example of probabilistic localization by using our discrete Bayes filter. And what you will find is that by modeling all of these as Gaussian distributions, it's actually easier to solve because a Gaussian times a Gaussian or a convolution of two Gaussian distributions will yield another Gaussian distribution. So what you will do is you see here that on the first step, you have a constant belief that you could be anywhere in the world. And then once the robot senses a door, you will have a piecewise approximation here that it is in front of either of one of the three doors. So that's why now you have these three spikes of this Gaussian distribution when it senses a door. Then as the robot moves, it normalizes and smooths those three probabilities, such as moving away from each of those doors. Once the robot navigates in this one-dimensional corridor and now detects a second door, it now is able to increase the probability of being at the second door based upon the sensor data, as well as the robot's motion in the hallway, and that's how it's able to localize. So once again, in the first step, you have a belief that it's constant, that after that first observation, the likelihood is that it's some kind of constant integral. But then when it goes to the next step, it's a convolution of that observation with the previous belief, which is what happens here with this integral. And based upon that convolution, that's where you come up with these three Gaussian posterior beliefs of where it could be. Then as it moves, it continues, but it's still yielding a Gaussian result, but there's some smoothing based upon this integral here and the constant. And when you combine all these results of the sensor data as well as the previous belief and the robot's motion model, you're able to get the robot to localize at the second door. So here we have a discrete Bayes filter approximation as a piecewise constant, where you now notice that our posterior beliefs are represented as these discrete values or these bins like a histogram. So once again, when the robot first moves in the world, it's a constant posterior belief that it could be anywhere. So we have this constant value. And then once it takes its first sensor reading and it detects a doorway, we now have the observations based upon the Gaussian distribution around the three doors. But then we also have the beliefs that are going to be convolved with those, which would also yield another Gaussian value. Then as the robot moves, it smooths out those values, moving away from the doors. And we then have that convolve with our new observation that the robot has arrived at a second door. And so based upon that, the robot is now able to localize at that second door. And then as the robot moves, we notice that that belief of where the robot is in the world moves with it. And so here we have our discrete Bayes filter algorithm. So we want to find the belief that a robot is at a certain location in the world by giving a data point. So first we initialize our normalization constant to 0. And then if our data is a perceptual item, such as sensor data, then we use a for loop to iterate over all of the possible next beliefs given the probability of a sensor data given the robot's current state times the belief it's in that state. And then we increment our normalization constant based upon that value. And we do this for loop for all possible locations in the world. And then from that, we are able to normalize this new belief by dividing out the normalization constant. Or if our data is given as an action item, such as an odometry-based or velocity-based movement in the world, then we do a for loop again where the belief that the robot is at a current state is found by summing the probability of the robot given the motion in the previous state and the belief of the previous state. And then once we solve for all of those, we can once again return the belief that a robot is at a certain state in the world. So this piecewise constant representation is a more computationally tractable way for the robot to determine where it is in the world. So assume we have a robot that lives on a plane and must always know where it is. So the robot contains 3 states. The location is X and Y and the orientation is theta. So we're going to need a 3-dimensional histogram in order to represent the robot's state space. So the way that we show this here is by these planes where X and Y are each of these grids. And then the vertical axis would represent the orientation or theta. So this bottom plane could be anywhere the robot is in the world, X by Y, but only for a 0-degree orientation. And so this next one up, for example, could be 30-degree orientation. The next one up could be 60 degrees, etc. So what you see here is that the vertical axis is the orientation. And you can quickly see that, for example, if this was a 20 by 50 meter grid with a resolution of 10 centimeters and 1 degree resolution, we could very quickly get to 3.6 million data points. So this becomes very computationally expensive very quickly. So robots would then have to either sacrifice onboard memory or computational power in order to implement something of this magnitude. So there are some ways that we have to be able to simplify this calculation. So some of the ways that we implement this is to update the belief of the sensor data to carry out the normalization to iterate all of the cells of the grid. And we will see an example of this, especially when the belief is peaked, which is generally the case during position tracking. And one wants to avoid updating irrelevant aspects of the state space. So that means if you get to a peak value, maybe you stop calculating in order to save on memory, or to update only subspaces of the entire state space instead of the entire thing. So if you can use some prior belief or prior knowledge, like we know we have a robot that cannot fly. So if it starts out at 0, 0, there's only so far it could be in a certain time step, then maybe you only implement that one little corner of the world. And this requires us to monitor whether the robot is delocalized or not, because if the robot's localized and you have some idea of where it is, you can do this. But when you don't know where the robot is in the world, then you got to iterate over the whole thing. So you think about the kidnapped robot problem to try to figure out where it is in the world. So to achieve this, one has to consider the likelihood of an observation given the active components of the state space. So to effectively update the belief about a robot motions, one typically can bound our Gaussian model for the motion uncertainty and reduce the cost from, let's say, n squared to n of the number of states. So once again, only looking at a substate. So this can be realized by shifting the data in the grid according to the measured notion. So according to the data that you're given, you can then come up with some kind of kernel or Gaussian kernel to iterate over the part of the world that you need to use to determine the robot's probability of being in a certain state. And by doing this, you have fewer operations, so it's easier to implement. For example, in a 2-dimensional example where you have a 9-element kernel, then we would require typically to multiply 9 multiplications per cell. but we can go faster by doing 2 one-dimensional kernels, which makes 6 instead of 9 multiplications. So for example, if we now know the robot has to be in this 3x3 subset of the world, and we're going to then put our probabilities over it, then instead of doing the Gaussian of the 3x3, then you can just do the Gaussian only of the rows and only of the columns, and then add those two together, and that will give you the same result, but you have only done 2/3 of the calculations. So for Gaussian-based localization, we need the robot with laser readings. And if we know the reading tells us that there's a high probability that the robot is at a wall, then we can then do our probably mass distributions, but we could do them only around the walls in the world to decrease the number of calculations we have to make. And then from that, we come up with the histogram. So here we have an example of that, where the robot has sensed that it's near a wall. So then if you notice that only the posterior beliefs that are near a wall have the darkest values, showing that those are the probabilities of where the robot could be. Then as the robot moves around and continues to take sensor data, maybe the robot now can detect that it's actually in a corner of the world. So now the posterior beliefs would only be the darkest at places where the robot could detect that it's in a corner. Or finally, if the robot then moves back a little further, the robot is then able to localize that it was actually right here in the world based upon detecting a wall, a corner, and then moving to detect another object. So the best way in order to localize with this grid-based method of localization is to incorporate one movement and one laser reading, have the robot move, and then as you determine more things about the world, you can come up with a subset of the world where you need to iterate over it with the kernel or iterate over it with the probabilities in order to determine where the robot is, where the probability of the robot's mass is then localized a little quicker like that. So once again, you see that as the robot turns around and moves back and takes more laser readings, it was able to localize here at this space in the world. You could also do the same thing with sonar. So let's say you have a sonar or 22 sonar ring around a robot. And based upon that data, as the robot moves, you want to try to localize. So what we have here is a robot is moving in the world, and then at locations A, B, and C, it collects this data, and it's going to try to use that data in order to localize. Here's a map of what the world looks like. And so here we have position A. The robot is in this upper hallway up here, and so it sends back sonar data at that location. And then we have position B. So now as the robot is moving, it's determining places that look similar to where the sensor data indicates in the world. And it's now down to, instead of all these possibilities, there are all about 1, 2, 3, 4, 5 places it could be in the world. And then finally, as it moves again, it's able to localize and realize by position C that it was actually here. So another variant for doing this that helps with computation is called tree-based representation, which is octrees or quad trees, where when you're close to where the robot has sensed that it is, such as if it's in a corner of a world, then you make the data as discrete as possible to try to help the robot to localize. But there's areas of the world that don't sense any walls, then you know the robot couldn't possibly be there. So then those areas would be big values of free space as shown here, where you concentrate your Gaussian distribution, your convolutions and your calculations over the possibilities for where the world could be, for where the robot could be. There's also another example of the octrees and quad trees in three-dimensional space, where now you have it efficient in space and time and multiple resolutions in 3 dimensions, where you're now considering X, Y, and theta and time. But once again, you would have it pixelated the most at the places where it could possibly be based upon the sensor data. So in summary, discrete filters are an alternative way of implementing Bayes filters. They're based on histograms for representing the density. They have huge memory and processing requirements. So you always want to come up with some strategies to try to minimize the amount of memory used or computational power used, such as doing quad trees, octrees, or using Gaussian kernels to only iterate over the parts of the data that are relevant to the current localization position. Notice that you can easily recover from localization errors because just as we started constant here, as the robot moves around, it will start to increase its probability of being in certain locations given sensor data or motion data. And the accuracy obviously depends on the resolution of the grid, but there's got to be a trade-off between the resolution of the grid as well as the computational efficiency and power, because the smaller the grid, the higher that goes up. And notice that there are some special approximations you need to make for this approach in order to have dynamic memory and computational requirements. And so this concludes lecture 5-1 on discrete base filters. I hope you've enjoyed. Watch more than once, take lots of notes, and have a robotastic day.